Okay, let's take a look at a problem that'll give us some exercise on this concept of the standard normal distribution and how we can use it to relate values and other distributions together. You're not given a data file for this problem, but we can build what we need in Excel. So in the problem, you're told that drivers on interstate highways in the U.S. Don't observe the posted speed limits. Let's assume that the actual speeds are normally distributed with a mean of mu and a standard deviation that we know, which is 5 miles per hour. So given this information, we want to answer some questions. And the first two parts of the problem say, well, look, given a percentage of drivers that drive above or below a certain speed, find the mean if we know the standard deviation at 5%. So we'll take a look at that first. And then the last part goes on to ask us, hey, supposing we're given a pair of simultaneous conditions. So in one case, we know a certain percent of drivers drive above some speed, a certain percent drive below a certain speed, a pair of conditions. If we want to find the mean and the standard deviation, given that they're both unknown. So we have, in essence, two simultaneous equations, right, in two unknowns, to go back to some earlier math. And here's what we're going to need to be able to relate in our minds. We're going to need to recognize that if I know the percentage of drivers that are driving below a certain speed, and if I don't know the mean and standard deviation, well, I can't use that percentage as a cumulative probability to find my actual value, but I could find the corresponding z-value, right? Because I don't need the mean and the standard deviation both to find out the z-value from the cumulative probability. So we'll use the norms inverse function and my probability, which is my proportion of drivers driving below that certain speed, to find the corresponding z-value. And then I can use my standardization formula, if you will, to say if I know the value and I know its z-value and I know the standard deviation, I can easily solve for the mean. So this is the approach that will help us get through the first part of this problem. And then it turns out we'll have to do this twice at the same time if we don't know both the mean and the standard deviation. So I've created a file in Excel where I've captured some of this information, and I've put in some placeholders for where we can answer this problem, and you'll see this file and you can work along with it. It's called Speed Calculations. So what does part A say? We're told if 40% of all U.S. drivers are observed traveling at 65 miles per hour or more, what is the mean, mu? And this is, again, given the standard deviation of 5 miles per hour. So what are we talking about here? Let's bring the our applet back in here. So we're saying, supposing I have a normal distribution, and I've just put in a number here of 68%. I don't know what the mean is. This is what we're trying to find. The standard deviation is 5 miles per hour, and I'm showing here shaded. I'm showing the probability of being of driving at 65 miles per hour or above. Okay, so and that probability for a mean of 68 is 72.5%, 72.6%. But we're told, so this mean of 68 is obviously not the correct value, because we're told that 40% of drivers drive faster than 65 miles an hour. So I need to essentially shift this distribution to a point where that value of 65 miles per hour has only 40% of the distribution falling above it and 60% falling below it. So essentially I need to shift this entire distribution down to the left, and I can do that by trying smaller values of the mean. So I could use trial and error here. Okay, so 68 isn't working. What happens if I put in something like 60? Okay, well, now the probability of being above 65, if the mean is 60 and the standard deviation is 5, well, that's only 15%, right? 16% roughly. So somewhere in between there is a value I'm after, and I could kind of, use trial and error to get to it. But let's see if we can do this analytically. And we should be able to, right? Because we know that 60% of drivers drive slower than 65 miles per hour. All right? So that value, 65 miles per hour, has to have a z-value that we can calculate using the norms inverse of 60% as my cumulative probability. So I'll put that in here. Equals norms inverse of 60%. And I get a z-value of 0.2534. So that means that this 65 is about a quarter of a standard deviation above the mean, whatever that mean is. Okay, well, if I take that formula I had, z equals x minus mu divided by sigma, and I solve for mu, if you will, I just turn the formula around, I end up with mu being equal to x minus the product of the standard deviation and the z-value. And I can use that formula and plug it in, because now I have everything I need. I know my x value is 65 miles per hour, my standard deviation is 5 miles per hour, and I now have the z value. So I can find the actual mean using this formula that I've put in the comment here, which is equals my x value of 65 miles per hour minus, open parenthesis, my standard deviation, which is 5 miles per hour, times my z-value that I just calculated. And I get a value of 63.73 miles per hour. And let's see on our applet, does that pan out? So instead of 60, I'm going to say 63.73. So I'm going to plug that in as my mean. Standard deviation is 5. And I'm going to get, it calculates my probability at 39.97. So again, I could add another, 733. Yeah, there we go. So if I take out my mean to 3 decimal places, I get a probability of exactly 0.4. All right, so we're able to solve this. This is the mean of that distribution that has a standard deviation of 5, such that 40% of drivers drive faster than 65 miles per hour. Okay? You can do exactly the same thing for the second part of the problem. In the second part of the problem, you're told 25% of all drivers are observed driving 50 miles per hour or less. What would the mean be? Again, given a standard deviation of 5 miles per hour. I'll leave this for you to play around with, but the approach is the same, right? We now are already given the cumulative probability, 25%. So 25% of drivers drive slower than 50 miles per hour. What would that z-value be? Well, it's just going to be norms inverse of that 25%. And then we can use the same formula to calculate the mean. All right, what about the third problem? The third part of the problem, it says, supposing now that the mean and standard deviation are both unknown. So let's say it's not 5 miles per hour for the standard deviation anymore. We don't know what that is. But it's observed that 40% of all drivers drive less than 55 miles an hour, and 10% of all drivers drive more than 70 miles per hour. So we're given these two simultaneous conditions. What would we need to do? Well, I've set this up so we can investigate this. Okay, same form as what we were doing before. 10% of drivers drive faster than 70 miles per hour, so 90% of drivers drive slower. Okay, the z-value corresponding to that 90% that drive slower is a 1.28. We just used our norms inverse function on 90%. Same thing we were doing before. Okay. And then I put in a placeholder for the miles per hour. I said, well, look, let's suppose we were at the same speed, standard deviation before of 5 miles per hour. What would the mean of that distribution be? Well, same approach. I came out to 63.59. Now, I don't know this for sure. I'm just taking a guess. Okay. Well, if I plug that guess into the next condition where I'm told that 40% of drivers drive slower than 55 miles per hour, and I do my same calculation here, and I make the same guess of 5 miles per hour for the standard deviation, but when I plug in my formula, I get a different value for the mean. Okay? What I need to find is the right pair of standard deviations and means, basically, that correspond, that satisfy both of these conditions. So it can't be 5 miles per hour as the standard deviation, because that's not giving me the same value for the mean. So what I need to do is try different values of this of miles per hour until these means are the same. And again, we can do that by trial and error. You could do this analytically using, if you know how to solve simultaneous equations, if you remember that from algebra, that's fine. I want to show you a method in Excel that will help us do this, where we can have Excel do the trial and error for us. And we may have seen this before, but it's using something called goal seek. Because what I need to get to is the point where I've picked a certain value for the standard deviation that lead me to the mean in both of these cases being exactly equal. So I've linked my my standard deviation together to the same value. So I plug in 5 here, it gives me 5. I change that to 6, well, it changes it in both places. 6 obviously isn't right either. But I want to find that value that I plug in here to cell D21 that makes these two values the same. The mean from my first condition and the mean from my second condition. And I'm going to do that by calculating what the difference is between those two means. Because if these two means are the same, then the difference between them is going to be 0. Right now the difference is 5.7 miles per hour. If I go to 6.5, it shrinks a little bit. So I need to go up as high as I can until I get these numbers the same. If I go up to 15, okay, I've passed 0. So here's I'm trying, again, I can keep doing this by trial and error. I could use a data table. I'm going to show you how to use the goal seek, because what I want to do is I want to tell Excel to just keep trying different values of this guess here for the standard deviation until the means are exactly equal, as shown by the difference being 0. And the way I do that is I'm going to click on my cell where that difference is, because that's the thing that I want to change. I want to drive that value to 0. I go to Data, I'm going to go under What If Analysis, and I'm going to go to Goal Seek, because I want to seek out a particular goal. So I want to set the value in cell F33 to a value of 0. And I want to do this by changing the value of my standard deviation, which I have plugged into this model in the first place in cell D21. So I'm going to change the values in cell D21. Remember, that's linked to my second standard deviation place with a formula. So I hit OK, and Excel should solve this for me and give me the right values that drive this difference to 0. And very quickly they converge to a point where I've got a standard deviation of 9.77 miles per hour and a mean of 57.476 miles per hour. So I've got the same standard deviation, the same mean in both cases. And therefore, of course, the difference is 0 because the means are equal. All right, so here's one way we can solve these simultaneous equations in Excel.